All right, everyone. So we're about to get started. So good afternoon to our speaker today. So I'm actually really excited. Dr. Gabriel Fernandez. So we just called him Gabe. So my good friend and also my former lab mates for our PhD Gabe. So Gabe got his PhD in mechanical engineering. So enjoy. So Gabe's work ran from developing modular delivery robot for LG electronics. Just last year, leading our lab to regain the RoboCup World Championship. So and also just share some fun fact about it. So he's a wonderful mixture from half Chinese, half Puerto Rican, raised in Hawaii, did a 2-year outreach programming from China, and also studied Chinese for another year at full-time university. So also an American football player. So, but let's see how he finally became soccer champion. It's all.
Oh, thanks, Ed. Thank you. All right, so today I will have this be a little bit interactive. So I have a lot of slides and a lot of material I could cover. And on top of that, there are some of my lab mates in here like Aaron, Norman, or Aditya who can definitely answer some questions a little bit better than I can. But as Aaron said, I helped lead the team to regain the RoboCup championship back in 2024, which was last year. And we had an exhibition match with Booster Robotics, which I think won this year. And we still beat them, right, Norman? I don't know the score, but Norman was there in the lab. So anyways, we'll get started. So we're gonna do a quick intro, a little bit about things at Romella or the lab that I worked at. Then we'll talk a little bit about RoboCup to give you an overview of how we, basically won our games and kind of the overall structure, hardware and software, and how that was consistent. And then we'll step a little bit into localization, which is something that I worked on and that we created specifically for RoboCup. And then we'll talk about how we go about from something like a game of RoboCup to kind of generalizing the process out a little bit further to have a higher impact, even though it comes from a very simple idea. So we'll get started. I'm from Romella, so is Aaron, at UCLA under PI Dr. Dennis Hong. We have alumni here at Big AI, several people. A lot of what we do at our lab is we build robots from the ground up and also control them, apply whatever algorithms we want to them, but we cover the full system. A lot of labs do not do full systems. A lot of labs just do partial or bits and pieces of the system. And we worked with notable people or companies, Netflix, NASA, I mean, you name it, we've probably worked with them at some point in time. So a few of the work, or at least things that I've helped out on. So this is the robot we played soccer with, but this is Artemis kind of initially in the beginning. I think we also worked on climbing robots. The lab also, I guess if this goes, this is like the modular robot that we designed and created that can latch and unlatch and move across different places to do pick and place. And then there's a classic picture with me and Aaron winning Best Paper Award at IROS way back in the day with Shren, or I don't know if Shren's listening, but he's probably online somewhere. So now I'm doing a startup with a couple of guys. We're still sort of figuring things out. We plan to be in multiple places, maybe China. We'll see. I think that's in future works. But yeah, let's kind of move away from introductions and kind of get into the meat of things. So RoboCup, if not a lot of people know, I feel like this audience knows, but maybe some people online might not know. It's an international competition where essentially robots play soccer against each other autonomously. I think the goal is to beat the FIFA World Cup champions by 2050, a game against humans and robots. But it's also expanded to a lot of different areas for search and rescue, at-home industrial and logistics. I believe China has its own league of a lot of different other categories now. So it's a very quick and expanding area. Just to give you some reference, this was pretty much a 3-year project. And we didn't start off winning or didn't start off at the very top. We actually worked our way up from the first year scoring 0 goals, second year scoring 2, and then the third year scoring 67. So for all of you thinking that it's a one-time thing, it's a long process for a lot of these things to come to fruition. and to give encouragement to those who have struggled in a lot of this stuff. But some of the highlights for our particular system, we had the fastest speed at that time, probably strongest kick, and even the most accurate, I would say. And we'll watch a few videos of that. And a very robust localization on top of all the other pieces that go along. So we played robot with Artemis. It's one of, I guess, our lab's premier robots. It stands for Advanced Robotic Technology with Enhanced Mobility and Improved Stability. One of its features, it was specifically designed for soccer, for this competition. My senior who designed the robot was very passionate about RoboCup, let's say. So a lot of it is designed to move quickly, to have a wide range of motion, and to have compliance, because I think you do need that for this type of robot. And it's just very fast and capable. We're nowhere close to, I guess, reaching its full capabilities, but yeah. So if you saw in the previous image, that robot from the waist down was basically all custom built, including the motors themselves. So we use quasi-direct drive actuators with a low gear ratio. This allows for, I mean, the main thing I would say is the speed and compliance while still maintaining some level of torque. Being able to have the high control bandwidth and basically high torque transparency, meaning that you can use current to estimate your torque. These are all very useful things, and I think later on we'll get into why that specifically might help with something like our model-based approach for walking or running or kicking. So just to give you a little bit of an idea for high control bandwidth, this is just a very, very early test of the motor moving back and forth. And then since we have short on time, I'll just start the other video. Impact mitigation, right? If you're walking or running, you need to be able to absorb your weight as the robot is taking steps. So in the lower body configuration, we have 5 DOFs with a 45-degree hip design to distribute the load between the hip roll and yaw. And the image down below is kind of a demonstration of the wide ranging motions that it can do. And in terms of a design heuristic, we're trying to move all the mass up to the center of the body and keep the lower body as light as possible. And we'll get into, I mean, very briefly, the linear inverted pendulum and trying to design that for our humanoid in itself, such that the overall design is consistent with kind of the modeling and the control we're trying to use for that particular robot, or for this particular robot. So we additionally had, I guess, a foot design because without, I don't know if you can see my mouse, maybe not. The little wings on the side, we wanted to increase the range or the area in which we can kick the ball. Otherwise, our feet were too thin. So having thin feet, you'll have smaller contact and a higher chance of missing or whiffing the ball. So we increased it, but the reason why it looks a little funny is because in competition, other robots will be stepping on your foot. So this essentially folds down, so it angles down, so other opponents would kind of roll off. So it's flexible in one direction and not flexible in the other. So overall, Artemis has 20 degrees of freedom. It weighs 37 kilograms. So I would say relatively on the light side, and its height is 1.42 meters. And again, completely custom from the lower waist down. All right, sorry, I'm speeding through this because there's a lot of material that I want to get through, but feel free to pause me if you want. But we talked a little bit about the hardware. We'll talk a little bit more about the software and give like an overview. I think for a lot of cases, I think the one thing that's missing from a lot of architectures is this proximity component. Essentially, we have vision and we use machine learning to determine features in the field. But when this fails, this comes in and see. So anything that's too close, it'll be able to detect that, hey, there's an anomaly in front of me, maybe a robot, maybe a person, I don't know. But it's being able to catch those cases where I think a lot of people failed to incorporate something like that in the competition. But as you can see, everything's flowing from hardware vision into localization, into proximity, which all feeds into the high-level planner, then back to the mid-level planner and locomotion. This is, by no means the perfect architecture, but this at least gives you an idea of how we organize everything. So I guess one of the running heuristics in how we designed things as well is for a lot of the lower level control, we tried to have it at a much higher frequency. And as we got up the planner, so we had a lower level control for locomotion, we had a mid-level control for trajectory planning, and then we had a high-level goal for stating essentially the desired goal or state, final goal or state you wanted to be at. And each one of these ran at different frequencies, with the lowest level control running the fastest, actually, the mid-level second fastest, and then high-level quite slow. And our modeling as well kind of reflected that. Low level, we basically had full state control. Mid-level, I think, was slip or point mass, but the modeling got simpler and simpler the higher up we went. Which I think the idea was a lot of our opponents were artificially slowing their algorithms down to a certain degree, while we were trying to push as fast as we can, but organizing it in a way that everyone can solve independently. So quickly, locomotion overview. I think very simplistic, but just to give you an idea, we had something to determine our gait cycle, basically how frequently we wanted to take our steps. We had the lip model or linear inverted pendulum to determine where we were going to take our steps. And then we had a swing trajectory in which how do I swing my leg from one step to the next? And that fed into a whole body controller back into the robot. So with the lip model, we feel like it fit Artemis quite well. Again, I said a lot of the mass was redistributed mostly in the hip, right? So if you think of the linear inverted pendulum, you can feel like Artemis does a good representation of that on the design side. So again, this consistency, not only saying, oh, software handle this one thing, we really wanted to integrate both the design of the hardware as well as the software. The swing leg trajectory, we just used a sixth order polynomial. And if you're wondering, later on we'll watch like videos of the kick. We just adjusted that polynomial to do a little stab at the ball before landing in the correct spot. And how far we decided to, basically stab at the ball would determine how hard it would kick as well. So this is a little bit of just the robustness. Yeah, this is, and this is the kick. So not bad, not bad. So we're gonna step through each component. I'll try and get through this quickly as well. But vision, we basically had feature detections on the field. So we're looking for specific landmarks, whether that be crosses on the field, corners on the field, any sort of T-shape marking on the field, and we'd use this for localization and other things like that. It would also detect robots and opponents from the RGB frames. So that was vision side of things. And earlier I had mentioned proximity, where it would catch every time vision would fail. And in this case, we only use the depth information for proximity. This is assuming that I cannot detect that there's an opponent in front of me. Maybe the opponent is occluded. Maybe I only catch like half of its arm of the other robot, but that would raise a flag that there's an anomaly specifically in this area. And that would allow our overall detection rate to be a lot higher than what you would normally get in these competitions. So going on to the next thing, again, stepping through this kind of quickly. We had localization. And essentially what you're doing in this case is you're taking the field markers from vision, right? I said vision, you were trying to find kind of the crosses on the field, the T landmarks. In this case, the T's are represented by pink, the corners by green. And then from that, you can triangulate your position of your robot. And yeah, we're publishing this in humanoids, so you can also read this online as well. This is just to give you an idea real time what the robot is seeing in terms of feature detection and how well it's localizing on the field. Yeah, and there's Norman's back there who's featured in the video. The mid-level planner, we decided to basically, I guess people here aren't familiar with visibility graphs, but changing the problem into a graph search problem. Because the most optimal path would be along the edges of your obstacle, not some random thing. So, and you can build in slight cushioning around your obstacles as well. And we just found this to be a lot more efficient in solving, breaking up the problem into one, figuring out the optimal trajectory, and then two, kind of trying to give yourself enough space in case, it's a competition, so things are moving all the time. So we added an optimization portion to, I guess, the trajectory after we figured out the optimal trajectory, which allowed it to solve a lot faster, and I think helped during the competition a lot. So this is kind of like yeah, but even though these are cardboard boxes that we're not even really detecting, it's still doing a pretty good job. This is in coordination with proximity and a lot of the other stuff that I mentioned. So high-level planner, very simple, simple behavior tree. Our behavior tree is kind of large, though, towards the end of the competition. But I think one of the things that I'd like people to take away is, even though some of the components were simple, in coordination with each other, you can get really complicated or impressive kind of results. So I think in this one, it's one of my favorite clips because, I'll go back and explain things a little bit more in detail. You can see that girl, how impressed she is on the slide. But I'll replay this. Oh, let me go back. No. So let me just play this. So here, one of the impressive things is how fast I turn and then how fast I kick. Sorry, I don't know. Let me try this again. Yeah, how fast I'm going to the ball. And if you think, so 1, 1,000, 2, 1,000, 3, 1,000, like how fast it takes to kick. And then let me pause right here. So I'm taking a kick from half the field, right? With an open goal, I'm actually aiming towards the center. And if you look at this shot, like to turn that fast, hit the shot, and for the ball to end up right there, like you need to be like kind of accurate, and your entire system needs to be running a lot faster than I think a lot of systems today. But that's what I found really impressive about this specific shot. And this one, I feel like you get a more complicated behavior than you would expect. So it detects a robot, it's in front, it just pauses, right? It's waiting. Now the other robot's going around, but our robot comes in kind of underneath, right? And just kicks the ball to create space, right? And again, very quick kicking time. It doesn't take a lot of time to think, right? Where I think a lot of other robots take their time and to get that accuracy too, I think it's quite impressive. I think this is Aaron's favorite clip, and I think it's my favorite clip too. We had a bug actually during the competition where we'd go to the old position of the ball. So we overshoot, then accidentally almost score ourselves, right? And you have to imagine there are like 4 or 5 different people in the goal, right? And it's able to clear the ball out, and pretty quickly as well. So I mean, these are some of the biggest highlights, again, from something very simple to getting to this point, right? I think was very impressive. And then, we won and people were very relieved. It was a lot of pressure, and it's nice to see everything pay off. And that's us. But okay, so that's part of the talk. We can, I'll try and go through a little bit more depending on time, and see how people feel. But I'm gonna start to talk more about localization and that particular or part of the problem. And then I'm going to talk about how we generalize that into something a little bit bigger. I don't know if people had questions before I moved on. If not, I'll just move on, and maybe towards the end we can take more questions. So clap localization. I think on the surface, this is a very simple approach. Simple doesn't necessarily mean bad or less powerful, but very simple on the surface. As a matter of fact, so simple, some of the reviewers for the first paper were just like, this is too simple. Anyways, let's kind of get started. So the idea is we're observing, maybe in this case, a T feature, a corner feature, which is represented by an L, and a G feature, which is represented by the go. Now, the question is, given a lot of noise, how can we determine that this is the actual spot we are on the field? Because you can be in any maybe 4 or 8 different spots depending on the noise level. So for example, if I see a T and the L and I have no noise, I could be in 4 spots in the field, right? Now, if I see a T and a G, right, I could be in another 4 potential spots. And if I see a G and an L, another 4, right? But if I start stacking these up, what I'll notice is some of them will start to group together while others will start to spread. So what I've done essentially here is stack all the different 2 observations that I got up together, and I've eliminated 4 possibilities to only 2 possibilities. So like a 50-50 kind of a toss, right? We can carry this out for any number of observations we have. In this case, just the ideal case, we assume we've observed all field features, and this is all the potential spots that I can be on the field, given that my robot is in the corner where it's kind of red. Red is the previous pose. The yellow stands for, I guess, a very high number of estimates all grouped together. As a matter of fact, 52% of all estimates lie in one of 2 positions. The rest is just noise, or they don't group together at all. Let me kind of move on. On top of this, we added a component. So we know that once we do these estimates, there's a high level of grouping or high density of estimates that are very similar to each other, and the rest spread out. So what you can do is kind of cluster where these high density points are. And that's what we did. And we have 2 types of clustering. One is local clustering and one is global clustering. Local clustering says, given the previous state, let me look locally around me and see how many estimates I have, and to use that, which helps in a lot of ways for you to be more accurate very quickly. However, it comes at the risk that you'll begin to diverge because you're just taking in local data. Global clustering says, let me take in a history of estimates that I have, and from that, try to gather as much information, meaning it's a little bit slower to react, but it's much more robust to noise because you have much more estimates. So as long as these 2, I guess, groups of clustering are relatively in the same area, we say we're okay. If they start to diverge for a long period of time, then we say, oh, okay, our local clustering started to diverge. Let's reset to where the global clustering is. And I think this helped a lot during the competition. I remember looking at other people's computers, seeing what they had. We had competitions where we had to be on the same team with another team. So there are like 3 or 4 robots going against another 3 or 4. And there's just a big mess. But our localization still withheld all that noise. And a lot of people were surprised. I think, again, this is a very simple method. This gives you, so we saw that clip before, but this gives you an idea of where all those estimates are lying as we're going about. But you can see that bright yellow spot is fairly consistent in most cases with only 2 options. If you can eliminate a lot of your estimates down to 2 options, you've done a pretty good job, in my opinion, especially on a highly symmetric field with a ton of noise. So what we ended up doing for CLAP in particular, we ended up comparing this to a couple of other algorithms and just pumping a lot of false positive data onto the field. So, just random noise on the field just to see how robust it was. So the 20%, 40%, 60%, et cetera, that's the additional noise or false positives that we're pushing into this particular trajectory. And as you see, as the noise increases, clap stays pretty much the same. Whereas the other algorithms begin to diverge and diverge a lot, potentially. You can see with trajectory 2, you can see with trajectory 3, clap, for the most part, is very, very robust to noise. We can skip this, I think we don't need to do this. But even taking a shot like this is really hard for robots from that angle with the right side of your foot. And in my opinion, that has to do, oh, we saw this localization. But a lot of people said, okay, great. You've created a technique for basically a toy problem, right? This doesn't work in 3D, or like, how are you gonna do this? Like, what is the point? It's great that it works in RoboCup, but like, how can I use it elsewhere, right? So I think with a little bit more time and thought, we actually realized that it was very similar to a few other algorithms, and not necessarily within robotics itself, but in image processing, specifically when we're talking about ransack and hue transforms. And these are algorithms, or ransack in particular, is widely used to reject noise or reject outliers. And I'll kind of cover this again. But what clap does is it basically looks at your output and it tries to do matching with other points on your output, given a subset. We'll talk about this more. I just want to give you a quick overview. Whereas ransack is trying to find a model, and it looks at your input to check whether your model is correct or not. And then hue transform is trying to find a model, but it uses your model parameters to try and check whether you're correct or not. So this is getting into a little bit, maybe subfield that maybe people in this room aren't quite familiar with. But again, I'll walk you through everything, and I think you should be able to understand. So what ransack does, if we're trying to fit a line in this case, it picks out 2 points, or the minimal amount of points that your model needs, and fits a model to it. And then in this case, it tries to look to see if there are other points in your input space, in this case, your input space or your black dots, and tries to see how close it is to your actual model. So in this one example, right, the number of points in red are considered close enough to the line to call them inliers, or we count them up. In this case, it's 6, right? And we repeat this, right? We fit another line to 2 points, and we count how many points are close to the line, right? And we continue this until it finds eventually 2 points that actually lie on what looks like a line. And the number of points is really, really high. So we pick the model with the highest number of points, right? Whereas the other points are considered as outliers, or we reject them, essentially. So we say this is like a consensus on input space. We're finding a model. It's very robust and very simple in nature, but it's really slow. A lot of these algorithms, it takes time because you're iterating over a lot of the space. But as you can see, also, most of your data lies on that line anyway. So there's a good chance you'll hit that earlier rather than later. If we go to hue transforms, it's a little bit more confusing to think about. We're taking the consensus on your parameter space, trying to find a model. So we're trying to find that line again. In this case, I got rid of a lot of the noise because it would just be too confusing. But essentially, let me just go to the next slide. I think it's a little bit easier to understand in the next slide. We're looking at your image space, and what we do is we transform that to your parameter space. So if in your image space, the equation is y equals mx plus c, or mx plus b in some people's case, in your parameter space, it's c equals to minus mx plus y, right? So points in your image, this is image processing. Points in your image space gets transformed to lines, and lines in your image space gets transformed to points. But what you can see with the black dots in your image space, they all create lines that intersect at one single point, right? And at that one single point is where the true line lies. So what you're essentially doing is you transform everything into your parameter space. Then you quantize this or build buckets, and you count how many, I guess, points are in those buckets. And the point with the highest, or the bucket with the highest number of points, is your line in this example. I hope that's clear. I think when you start thinking about this, this gets a little confusing. Clap, on the other hand, is, I would say, what Hue Transforms does is more similar to Clap, but the way Clap does it is more similar to Ransack in a way. So what Clap does, it still picks 2 points, it fits a line, and then it says, I don't care about the model itself, I just want the output. Maybe I'm only interested in X naught in this case, right? So I pick an X naught, right? And then I say, okay, my line gives me this point with this X naught. I do this with another point, right? I'm iterating over it again. And then I draw another point, another point. And what you can tell is because you have a high number of points that lie along the actual line, you have a high cluster of points that actually lie exactly where you're interested in. And I've kind of reduced the problem from almost like in Ransack and Hue Transforms to a 2D, in this case, to a 1D, because all I care is about the outputs. I'm only considering where all these points lie on a single line, essentially. So this is kind of getting to almost a very, very general technique to I guess, get rid of noise or reject outliers in essence. But the thing is, you can even have it be more general. With that being said, I'll get to that to the next slide. Sorry about that. But anyways, as a recap, Clap is trying to find an output, doing a consensus on the output. Ransack is trying to find a model, doing a consensus on the input. And Hue Transforms are trying to find a model, doing a consensus on the model parameters. Let me do a quick overview of highlights and things. I think we're still doing some work on this. So this is just my opinions right now. We haven't quantified a lot of the results yet, but we're getting to that. One nice thing about Clap is it doesn't care about models. So a lot of the other stuff cares about model parameters. And in this day and age with AI, if you need to care about your model or your model space, the problem becomes very hard. Depending on your dimensionality, right? If your model dimensions tend to be a lot higher than your input dimensions, which tend to be higher than your output dimensions, usually, not always. But if you can work in your output dimension space, it could run a lot faster. It doesn't track, you don't need to track models, you don't need to compare inputs or model parameters. And we saw it gets at least similar or better results to Ransack in many cases. And it's quite accurate if you know the output distribution noise. I think that's another additional highlight. That's pretty nice. So if we're talking about more generalization, what actually is interesting, it really doesn't matter where you want to look or how you want to do consensus, right? You can pick any of these combinations to do like whatever you're interested in and to do consensus on. Any of these combinations. It just so happens that Hue Transforms and Ransack are a specific combination of this, but you don't have to limit yourself to specifically these 3 form factors of this type of algorithm. So we do have some early results for 3D localization because now we don't care, right? All you need to do is sample, in the 3D case, sample 3 points, estimate, and keep doing that. And your cluster should naturally kind of be dense in areas that are true. As long as the data you're receiving is consistent with whatever, in this case, field map you have ahead of time. I think I have video. Yeah, so, and this is early results. There's a lot to clean up. I believe the guy who's working with me had a few bugs in his code, but it's at least working in 3D, and Clap tends to be a little bit faster than Ransack in terms of noise rejection, which is very nice. So we don't have to limit ourselves to robotics. We actually started to do image processing tasks as well. So in this task, we're doing image stitching, and essentially you have 2 different images taken from 2 different points of view. Let me see. Okay, I'll try and finish it. 2 different points of view. The true transformation is nonlinear, but you approximate it with a linear transformation. And then you try and match those images together so that it gives you one image. And we'll see a little bit of this. So for example, you have these two images taken from two different perspectives. We find a lot of features. So I guess we use SIFT in this case. If you're not familiar, essentially, it's an automated way to find features within an image, and then we try and match them. And we want to try and estimate the transformation. So we do the transformations on each of these images separately, and then we combine them to get a combined image overall. So this is, I'll go through another example just to give people an idea who are not familiar, right? We're finding a lot of, I guess, features between both of the images that you can find. We match them, estimate the transformation using CLAP, do the transformation, and then we combine them together to create one kind of consistent image, right? So we did that with a bunch of different images, and at least early results, it would suggest that we can find a better solution faster than Ransack in terms of the number of iterations the algorithm needs. But again, this is early and we need to run more tests. And yeah, I guess back to the overview, this is a family of, I guess, consensus or consistency algorithms. It's fast, it's very easy to compute, very easy to for a high level understanding. But I think it'd be useful for a lot of fields. At least it was useful for us during our competition in terms of rejecting noise. And it's a very general tool. I think that's one of the nice things about this. And it's very simple to implement. It's not very, very difficult. And then references for people who are interested. And that's it. Okay, I am out of breath, but thank you. If there are questions, I know I covered a lot and I tried to speed run a lot of this. Feel free to ask, or if there are no questions, that's also okay too.
And thank you for that presentation. I'm very interested in the localization process.
Oh, okay.
How do you concern the apps or point out that get from the camera, the information?
Yeah, so I guess specifically in the tournament, we would say, okay, that's a cross. And then I would get the distance from me to the cross to make an estimate of that way to build basically a relative map to where my camera is facing. And then what I would do from that is, given I have a relative map and I have a true map, I would match those up together. And then that would tell me where I'm on the field. So at any given time, I have a relative map, and then I match that with the true global map. Does that make sense? Or another way to think of it is, so if I see two landmarks on the field, I know the distance between those two, right? And then I have the true map and the distance between the landmarks on the map, right? Then I do a search, right? Which one has that same distance? And if I know that, then I can back up where I am in terms of an estimate.
Example, lot of perspectives in the true map. To find the right, the true perspective and the perspective from the camera. Yeah, so I guess I'll go one step further is I don't need to sample because I know the map ahead of time. I create a lookup table or dictionary that says it should be about this distance. And then I add in a little bit of uncertainty for the noise. So when I look at this distance, I know there's some noise. And then I look up in the lookup table for all the possibilities with that noise. And then I sample from that subgroup after that. Does that make sense? Okay. Thanks for the question. Anything? Don't feel forced to ask questions either. Actually, in the localization part.
Yeah.
But I'm also like looking into the make sure that I understand your approach correctly.
Oh, yes.
So you're basically doing a 2D feature detection
Mm-hmm.
and then use the 3D to estimate the distance between the robot landmark.
Yeah. So in the RoboCup case, everything was 2D. And yeah, so I see those 2 points. I know on relatively where I am relative to those 2 points. And then I search those 2 points in my dictionary of where they could be, or maybe go back to the slides actually. Sorry, I think it's easier with the images. So like here, right? I'm detecting a T and a G. I know this distance, right? In my lookup table, it says this distance is consistent with this distance, this distance, then I have to.
Yeah, but my question is about how to estimate the distance between like the image and the XI.
Oh, this distance?
No, the distance between the robot and the visual point.
Oh, so that's from the depth.
That's
Yeah, the camera has the depth data. So we basically, in our feature detection, we have RGBD. We find that feature, and at the center, we have a depth information there, and then we just take that essentially.
I'm wondering like if you have like quantified where's the major source of noise. Is that detection? Estimation?
Yeah,
Which
yeah.
you can think of major source?
I would say it's from our learning model, just because when we're in competition, actually, a lot of different things can change throughout time. So for example, during the competition, it had lighting, like natural lighting in some cases. And during noon, a big bright spot would just move across the field slowly. And lighting conditions would change after days. On top of that, we had crowds sitting around. So even like kids holding soccer balls, we were a little bit concerned about. On top of that, there's even other games. So our robots could see other fields. So some teams got confused and started assuming they were on a different field. So you really, or people's shoes was another thing. I think during the competition, one team kept complaining that, oh, this guy's shoe looks like something. So really the noise can be almost anything just because you are in a real world environment.
Or maybe I should read this way. Hypothetically, if we change I place this thing April tag in every corner. So in this case, like, would you consider, I mean, like, would you expect like a significant decrease of localization? Or
So it could be almost the same. My concern would be like in the middle of the field when you're moving away from a goal, there's not a lot of features you can see in general, right? And if you happen, I mean, April tags are hard to mismatch, but for some, like you get one anomaly that says, oh, I think that's an April tag, right? That destroys your entire system. So the concern is not so much that the possibility will be low. It's if that one, small possibility of an event happens, you lose the game essentially. So it's the idea of trying to be prepared for all kind of potential scenarios. Yeah.
okay, my last question is what this error accumulate? You implement like some forming strategy, like when do you restart estimator deal with the gap? Like,
Yeah. So usually, as long as we're seeing field features, it's okay because that'll correct any sort of drift from the IMU, right? So when I was talking about the clustering, is essentially what would happen. So this local clustering, because it's only taking local information, it doesn't have as many points. So any sort of noise can cause it to diverge a little bit, right? Whereas this new one, it's taking in a history of estimates. So if it's moving along, it'll have a history of estimates that it's moving along. and this would have a lot more points, but it wouldn't be as sensitive to, I guess, your most recent, I guess, testing. When these two clusters start to diverge apart, we know there's a problem. Because I guess they should be relatively close, but a little bit separated. And then we would say there's a lot of, I guess, safeties we put in because resetting localization can be a very powerful tool that can also wreck you during a tournament. But essentially that's what happened. Now we had other forms of global resets before where we said, like whenever we saw, I think it was X, three X's in the global field, we would check whether we're on the left side and the right side. We know we're in one or two positions. That was our initial approach when we generalized it to say any subset of features over history we can create. Yeah.
So like basically you still need like maybe like human supervision to determine like, hey, like we have the localizer is divergent and we reset it. So there's a possibility that we can have an automatic solution that like when the robot feel like its uncertainty goes really high, it can signal human supervisor, see whether we need to reset.
Yeah, I mean, in this case, once for us, our automatic solution, once that distance between the two clusters reaches a certain point, so that's the signal that and we would always go back to global because global was the safest one to make. So I do think there's a way to reset, and I do think it has to do with the features that your robot is detecting. It's again, I think the nice thing about these algorithms is you're doing consistency with what you expect to be. And if what you're seeing is not what you expect, you could potentially use something like this to flag that it means something is wrong, something. And I think this doesn't only have to be localization as well.
Yeah.
Any sort of flag for outliers is it.
That's my question.
Oh, thanks, Hans. No. Yeah.
First, I'd like to introduce myself a little bit.
Okay.
So I'm the former team leader of Team B. So I was in
Yeah.
And I think the most changing RoboCup is we have many more high performance roles.
That's true. Yeah.
That's correct. And I think what they take something bad into the game is the robot does not control the ball anymore. So the ball just goes everywhere. But as before, the robot can just pass the ball to each other.
Yeah.
It looks like more human something like this. So I think the new question about the robot software is we need a kind of a benchmark to redefine the game that maybe the ball needs to be manipulated. Not only that.
Yeah.
Goes somewhere. And also I think we may redesign the field like the Google they did they use slopes around
yeah.
the field. Then back
Yeah.
and continue the game.
Yeah.
So do you have any progress in defining how players can play soccer more well and more redefine the rules of the game?
Yeah, I think so. I mean, playing soccer better, I think, as you're describing, I think requires a bit more learning, which I think is fine and good. I think that's one of the ways Artemis, you can use some sort of hybrid model between model-based and some sort of learning approach. I think that's fine. I've already graduated, so I can't do any of that. I guess that's up to Norman back there, who I think he'll try eventually. I think as far as the rules, it's hard to say because I think for the full-size humanoid robots, it's getting harder and harder for labs to compete. And that's a sad thing for me to think about. I would almost like them to almost do like a shootout in soccer, where you're just demonstrating almost the mechanical capabilities and maybe something like learning to an extreme in one particular case, and then have a separate competition that has a little bit more, I guess, to get to the next stage. But like, if the goal is to plan to play against humans, and it depends if you're okay with a lot more companies being involved, which is not necessarily a bad thing. But it does start to get harder and harder for the actual researchers who are coming from smaller places to participate in them.
I think for it's hard to complete maybe I will ask that.
Yeah.
But there one maybe we can focus on building high performance goalkeeper.
That's true. Yeah. I would like to see more cooperation at a lot of these competitions, because it's a competition. A lot of universities don't cooperate too well because they see you see the other team as an opponent, right? But I do hope or wish that there would be more of an emphasis of working with other teams. I think that's a big thing that could go a far way, and also help a lot of research groups who might not have 5 robots or might not have X number of robots to do the competition. So I think part of it is, I guess, in terms of rules, I think it's good to aim to make it more lifelike, but at the same time, I want there to be more openness so that more universities can participate. Because I think right now, the level that it's increasing at is making it harder and harder for like the researchers to participate. I hope that answers your question. Okay. But thanks for coming. I mean, we'll talk more after. Anything else? If not, good. Oh, online. Oh, online audience. I don't know how to check the. Maybe I should. Oh, chat. Oh. No questions from online, at least not that I see right now. Thanks everybody for coming. I know.
So I have a final.
Oh yeah, final question. Okay.
Use. So because we have 2 robots,
Yeah.
we have information to develop the issue.
That would be interesting. We have not tried that. Rochan, are you listening? This is another thing you can try, Rochan, if you're in chat. That would be interesting, but no, we didn't try. I think right now, if you guys think of any other good application for noise rejection that we can easily try, we're trying to just work through several examples to just show how general and how well this works. But yeah. I think that's it. Thank you for everybody coming, and